So in this video, I want to extend the idea of spectral clustering and talk about how it can be applied in other scenarios as well. So it turns out that spectral clustering methods, including the algorithm that I just told you about in the last video, turns out that these methods work really well on some types of actual, like traditional design matrices, actual like XY point data, where again, we have our rows and our columns where the columns are features. It turns out that if we have a data set like that, we can still use spectral clustering to obtain good clusters. Well, how do we do that? Well, if we want to use spectral clustering on a design matrix, we have to construct a graph from our data. So before, throughout this whole lecture, I told you, well, what if we have a graph? What can we do to cluster it? If someone gives us a graph, for example, how often roommates talk to each other. Someone gives you a graph, how do you cluster it? Whereas in this case, in this example, now we're given a data set, just a normal tabular rectangular data set like you've seen 100 million times in Data 100. Given that data set, let's now construct a graph from that data set and then cluster that graph. And then that will help us obtain a nice clustering for our original data set. And it turns out that if you want to actually do this spectral clustering in sklearn, for example, sklearn assumes that this is what you want to do. It doesn't assume that you're starting with a graph. It assumes that you're starting with a normal rectangular tabular data set. So now what's going to happen is that each row in our design matrix, each individual, is going to become a vertex in our new graph that we're going to create. And the edges between these vertices are going to represent how related or how close together that specific pair of points is. And we'll see a couple of examples of how to do that in this video. So here's an example data set. It's just 4 points. I've labeled them E, F, G, and H. And this is a normal rectangular data set. We can plot this data on a scatter plot like so. We have 2 features, X1 and X2. And if we plot the data, here's what it looks like, E, F, G, and H. We have 4 points here. So again, normal data set here. This is not a graph, at least not yet. We will make it a graph very shortly. So the first, I'll call it points to graph method, is to use what's called the distance matrix. So one way to construct a graph, as I've written here, is to have the edges be some measure of the distance between each pair of points. So maybe points that are really, really far away, we would say, well, those 2 points don't really, they don't have a strong relationship. They're pretty far apart. And points that are really, really close together, they're tightly connected. We want them to have a really, really strong relationship. So we'll need to calculate the distances between all of our points. So if we have our design matrix here, again, with 4 points and 2 columns, we can use this design matrix to create our distance matrix. And there are easy enough tools that you can use to do this. I think sklearn has this functionality. But the reason, or how to kind of interpret this distance matrix, is you can read rows and columns and it'll say, okay, well, what's the distance between E and G? The distance between E and G, I just go to the E row and the G column, it's 0.7 in whatever units this data set is. Or I could go to G and find its distance to E, which is also 0.7. If I want to find the distance between H and F, I could go down here to H and then over to F and see that the distance is 1.6. So this is also another symmetric matrix, like we've seen so many times in this lecture so far. So we take this design matrix and we can create the distance matrix. Here's a question for you. In our new graph, what should the weights of the edges be? Specifically, should the weight of an edge between the 2 vertices be equal to the distance between the 2 corresponding points? So to go back to our example, when I'm making this graph and I draw an edge between E and F, should that weight of that edge be 1.9? I guess yes or no, and why? So pause, think about it. I spoiled it right away, but the answer is no. And that's because in spectral clustering, larger edge weights should indicate a stronger relationship between 2 vertices. But if we have a large distance, then that's not really a strong relationship. That's a weak relationship. So we need to do some function that kind of inverts things such that smaller distances have larger weights and vice versa. It doesn't make sense for 2 points that are really, really far apart to have a really strong edge weight because those points aren't closely connected. They're not really related that closely. So what we'll do is to figure out what our actual edge weights are, we'll apply a decaying function to the distance matrix. So this function, it can be almost anything you want, but it has to have the property that as the distance gets larger, the result gets smaller. So that's why I say here, decaying function. So now, if we have larger distances, those will lead to smaller edge weights and vice versa. So a common choice, something, I think this is the default in sklearn, I'm not sure, but a common choice is to do e to the negative gamma d, where d is the distance, and then this gamma is just some constant that you choose. It's almost like a hyperparameter. If you just do e to the negative d, then maybe that's too strong or too weak of an inversion. So you can adjust that with this gamma parameter, hyperparameter, excuse me. But don't worry too much about it. So what we have here is we have our distance matrix. And what we can do is for each of these elements, we just do e to the negative gamma d, where again, d is the distance and gamma is just some number. And we get this result. Notice how I've still kept the diagonals at 0, even though if you did e to the 0, you would see 1, but I just kept them as 0 here. And now hopefully you'll notice that, for example, e and h, which are the 2 points that are farthest apart in the data set, now E and H have the smallest weight. Before it was 2.8, now it's 0.24, which is the smallest edge weight. G and E, which are the closest points together in this data set, now have the strongest edge weight at 0.7. And then you can see for the other edges here. So what we've done here is we've taken this distance matrix and just applied a function to it such that our edge weights, they're larger for points that are closer together and smaller for points that are farther apart. In this result here, we can call this an affinity matrix because it describes kind of how much each of these points like each other. G likes E a pretty good amount, so it gets a pretty high weight. H doesn't like E that much, so there's a pretty low weight here. So that's one way to do to create a graph based on our data. We look at the distances between the points. So here's what that graph looks like. So here I have E, F, G, and H. And I have edges between all of them, and the edges are labeled with the weights like so. So this is just the graph representation of the adjacency matrix or affinity matrix here on this slide. Okay. The other method, the other common method that's used is nearest neighbors. So it's all on one slide here, and we'll just walk through it. It'll take us a little bit. But another way we can construct a graph is to draw an edge, typo, is to draw an edge between 2 points if one of the points is one of the blank nearest neighbors of the other point. So in this example, we're using one nearest neighbor, but you don't have to use one nearest neighbor. You can choose 2 or 3 or 4 or 5 or 10 or whatever other number. The reason why I didn't give this a letter and I just left it as a blank is because there's already so many letters that we've talked about, and I just don't really want to confuse you any further. And we don't really care, like, we'll never see this number ever again. So that's why I just left it as blank. But if we want to construct a graph using one nearest neighbor, we can do it in the following way. First, let's look at E. We figure out, okay, what's the nearest neighbor of E? Remember, this is the distance matrix here. I guess I should have labeled it, but this is the distance matrix. The closest neighbor to E is G. So we can draw an edge between E and G. Now we can move on to F. What's the closest neighbor to F? Well, the closest neighbor to F is G. So we can draw an edge between F and G. Well, now what's the closest neighbor, what's G's closest neighbor? G's closest neighbor is E, but we already drew an edge there. So what we'll do instead is we'll just increase the weighting to 2. So in this case, imagine these edges indicate like best friends. So the best friend of E is G, and it turns out that G also considers E to be its best friend. So these are like reciprocating best friends. So that's why you have a weight of 2 here. Whereas F believes that G is its best friend, but G doesn't think F is its best friend. So that's why this edge weight is only 1 here, because G is only closest to F. F is not closest to G. So that's why this edge is weight 1 here. And it's a similar scenario for point H, or vertex H. So the closest neighbor of H is F. So we draw an edge between F and H, again, because F is the nearest neighbor of H. But because the nearest neighbor of f is not h, f likes g more than it likes h, then we're not going to draw, like we're not going to increase the weighting of this edge. This edge only has weight 1. So that's how you would do this if you just wanted to choose one nearest neighbor. Again, you could choose a different number. Here we only have 4 vertices, so it only makes sense to use either 1 or maybe possibly 2. But if you had a really large graph with hundreds and hundreds or thousands of vertices, then you could choose a larger number. And this is actually what you'll do in the lab. In the lab, there's a question that asks you to do spectral clustering. There's like some data that looks like rings almost, and you'll use the nearest neighbors method to create a graph and then cluster those data points. So there's 2 ways we can create this graph, right? One is this nearest neighbors, and the other is to look at the distance matrix. And notice that these are different graphs. This one, like the edges are different. Like not only like does the amount of edges change, but also the edge weights change as well. So 2 different ways. As for which one is better, well, it's just hard to say. The correct answer is just to try both and see which one does better. Yeah, there's no really right answer as to which one you should use. So just to kind of recap this section, the point of it all is that if we are given point data, so not a graph, a design matrix, not a graph, we can still use spectral methods to cluster those points. And we do that by constructing a graph from the points. We either use a function of the distance matrix or nearest neighbors. I'm pretty sure there's other techniques out there as well, but these are the 2 most common. However, a lot of times we don't actually care enough to draw the graph. Like we don't actually care what the graph is. We just care about the resulting adjacency matrix. Like we just care about this matrix. I didn't draw it for the nearest neighbors, but we just care about the resulting matrix. And these matrices, they're often also called affinity matrices, like I said before, because they describe the strength of the relationship between the 2 points. If 2 points have a very strong relationship, they like each other a lot, and that's kind of what affinity means. And as I said before, whichever one you choose is just dependent on your data. And if you have no idea, just go ahead and try both. So to end this video, let's revisit the spectral clustering algorithm. I've added a new step 0 here, which is if you are given point data, you can construct the affinity matrix A, aka adjacency matrix, affinity matrix, same idea, using either the distance matrix or nearest neighbors. And then you can continue with the algorithm as we've discussed it before, where you go ahead and calculate the Laplacian and the eigenvectors and select the eigenvectors and do k-means. But if you're given point data, there's like a new step 0, which is make a graph from the point data. So that's it for the slides in this lecture. The next video, which will be the last video, will be a case study demonstration of spectral clustering in practice. And I'll see you then.